which will determine the whole.
So I think
Yeah, the moment you say R goes to R cube, then you have no further choices. That fixes what
Yes,
R
sir.
square goes to, and that also fixes what
R
R
square.
cube goes to, right?
Yes, sir.
Okay. And the other choice is R can go to R itself, which will be the identity transformation. If R goes to R, R square has to go to R square, R cube has to go to R cube. So you have the identity and one more element in this group. So odd C4 will simply be Z2. Z2, by the way, is the default name for any group that you have with two elements, because any group with two elements is isomorphic to that one group, which can be labeled whichever way, but typically people label it as Z2 because that's easiest to remember that you have only two elements. Okay, so for small groups, in fact, basically you would have to look at the generators, and the only other real thing that you have to be worried about is the relationship between generators. So when you are talking of, we took a very simple look. Figuring out the entire automorphism group for a large group G is not a very easy thing to do. The basic rule is what we have said. Okay, you look at the generators, you see what happens to the generators, what possibilities are there, and what conditions can you have from the relations between generators. For cyclic groups, it's reasonably easy. For non-cyclic groups, for general groups, it's not that easy. It's not a very trivial thing to do in general. For small groups, it's easy, the way I did it. Or the way we did work this one right now. So any further questions about this?
Sir, can we say that the ought of G of any finite group of order n will be either isomorphic to odd G of any finite group of order suppose R will be either isomorphic to the symmetry group of R minus 1 or any subgroup of that symmetry group. Can we say that?
But that's sort of trivial, right? Subgroup. First of all, odd has to be a group, right?
Yes.
And you can always say that if you have a finite group, right, then identity has to go to identity. You have n minus 1 other objects to play with. So n minus 1 factorial is the largest number of possible permutations you can have there. And any automorphism has to be a permutation, right? Any isomorphism of a finite group has to be a, by the way, you all know this, right? A permutation is just another name for a bijection in on a finite set, right? You all know this, I hope.
Yes, sir.
So since automorphisms have to be isomorphisms, so they have to be bijections, right? So automorphisms must be bijections, but must be bijections which at least keep the identity fixed. So every element has to be in one-to-one correspondence with some permutation of n minus 1 objects, but not necessarily all of them. So it has to be some subgroup of Sn minus 1. That's sort of trivial. But it could be much, say, as you saw right now, Sn minus 1 usually is not what you have. For V4, for example, you did have S3. But that's a sort of, S3 is not big, because all possible permutations that you could have of the other 3 non-identity elements, they actually worked because of the restrictions did not really rule any one of them out. For C4, they did rule most of them out. Z2 is of course a subgroup of S3. That's a much smaller subgroup. So typically saying it's a subgroup of Sn minus 1 will be correct, but not really very informative in most cases. Yeah, but all the easier questions? Yeah, go ahead.
Sir, if if in a group, if no element is the inverse of itself, then I
Mhm.
think the art of G will be Sn minus 1 only. I mean,
Yeah,
I'm not sure,
true,
but that looks like
true.
that.
You're right. You're right.
Mm, okay.
But then
Sir,
that's true, but that's not really very relevant. We are not, look, frankly, we are not really interested in these questions that much because these questions will not really impact our final work. So we can, of course, spend a lot of time talking about abstract group theory notions. We will have to talk about some things because they are going to be useful. But but these deeper questions about what possible structures groups can have, etc., they are very interesting questions, but they are not really very relevant for the rest of the course.
sir,
Automorphism groups are, but exactly what kind of automorphism groups a group can have, that's not really that important for us. At least not at this stage. Yeah, go ahead.
sir, I mean, in the question two of this problem set five, I mean, we were supposed to describe this quotient group of this ON by SON. So,
Hmm.
I mean, I don't know. I mean, there are only two distinct left cosets, right? I mean, one is SON itself, and the other is set of all matrices with determinant minus one. That's true.
Right. Perfect.
Okay.
So,
I mean, no, no, I mean, I just
so
wanted to verify.
look, there are two parts to this question about describing a group. One is what are the elements? That is, if they have some concrete example, we're talking about a concrete group. In this case, we are, right? We are talking about a particularly concrete group where the elements are known. You started with, I think you're talking about the GLNR by SLNR thing, right? Oh no, ON by SON, right?
Yes, sir.
That was the
Yes, sir.
question. ON by SON. Okay, so or your original matrix had n by n orthogonal, original group had n by n orthogonal matrices. And the SON, of course, are those with determinant 1. And as you rightly say, that there are only two cosets here. So physical, so you could describe them at various levels. One is at the purely group theoretical level, you would simply say this is a two-element group, and there's only one two-element group. Case closed. Nothing else to be said. Right? EA, EA with only one possible multiplication table. Whether you call it a group with two elements EA or you call it Z2 or whatever, that's fine. That's a purely group theoretic part. But in this particular case, because we are talking of a concrete example, I would have expected that you would have told me what these courses mean. As you rightly say, one of the courses actually collect together all matrices with determinant plus 1, and another collects together all matrices with determinant minus 1. Okay?
Yes,
So
sir. So that
this
was all.
quotient
That was.
thing, yeah,
Yes, I mean, we
yes.
had to write that only, right? That these two sets
Well,
partition the entire.
these two sets partition the whole thing, but they form a group. That's important. So the group, I would expect both. I would expect Z2 to be mentioned because that's the group you get. And here the example, in this particular example, by the way, this question was deliberately kept open-ended because I would have wanted to see what you want to write. Okay, what do you think is good enough as a description? If this were a pure abstract group theory exercise, I would have said just saying the group is Z2 is enough. But because it is not, and you do have a concrete realization here, I would say the group is Z2. The full answer, which I would have liked, not necessarily the full answer that you would have given, is the group is Z2 with the two elements being identified with two cosets. The first coset contains all determinants, all matrices with determinant plus 1, all orthogonal matrices with determinant plus 1. And the second one contains all orthogonal matrices with determinant minus 1. That would have been almost perfect. Even more perfect would be one, if you add it to that, one has the rotations, the other has rotations and parity, or basically reflections. Non-rotation orthogonal transformations. So, okay, that third part is not essential, but that is the part which is really important for physics.
So, but then let's say if you take two elements from the second cos set, which is the determinant minus one, you sort of get you do a multiplication. You sort of get an element from the first cos set.
Right.
So
Why is that a point?
I mean, I don't know. I thought it is sort of interesting in some sense.
Yeah, it has to come. It has to happen here anyway because you have. Look, basically, what you are saying is there are two causes, right? And with two causes, You don't have much of a choice. You have only two possible. These are the only possible
Oh,
multiplication rules.
yes.
Right? But anyway, what you are saying actually is physically rather important. Two reflections, one after the other, does give a rotation. I mean, that's going to be very, very important when you talk about point groups. But it's rather trivial ultimately. Rotations are those which have determinant +1. Reflections have those which have determinant -1. And two minus ones multiplied gives you a +1 is something which you have learned since class 2 or something.
Yes, sir. No, sir. I was thinking about the physical implication of that.
The physical implication is important. It's going to be useful. The two successive reflections give you a rotation. It's sort of obvious if you draw it out, at least in 2 dimensions it's sort of obvious. In 3 dimensions it may not be that obvious. It's actually...
Sir, 3 dimensions, having a determinant -1 doesn't necessarily mean that it would be a reflection.
Well, it would be a reflection, it would be a parity and a rotation. So
Yeah,
it
it
could be
can
just
be a
pure
parity.
parity. It could be pure
But in
parity.
2 dimension it would work.
Yeah, even then it would work. In fact, this is going to be very, very useful later on when we talk about parity symmetry and stuff like that. This is a very trivial result at a mathematical level, but it's actually quite deep and important at a physical level. Now, as to what would you write in the answer to that question, it's up to you. I would want to see what you... Look, there will be several open-ended questions like this where the question may be interpreted in different ways. Sometimes it may be a mistake on my part. I may have just forgotten to make it precise enough. But most often it will be sort of deliberate. Right now, the assignments are really not meant to sort of straitjacket you into giving one answer to one question. That's always possible. There will be questions like that, but there will also be questions where you can sort of think about what you want to say. And saying everything under the sun is not necessarily good, by the way. Just because you have an open-ended question doesn't mean you write down whatever Mahabharata you think is good. Think of the relevant points. I also want to see what you think are the relevant points. Okay, go ahead.
So for the description part, showing just an isomorphism with the Z2 will be enough for answering the...
I couldn't even hear what you said.
I'm saying that for the description part, writing an isomorphism from the quotient group to the Z2 will be enough to show all the properties which you are saying.
In a way, yes, but the interpretation will not be there, right? That is, unless you tell me that that one quotient essentially are reflections on the other, rotations on the other, non-rotation orthogonal groups, orthogonal matrix transformations, you will not be able to interpret that later. As far as the answer to the assignment is concerned, any answer as long as it's not wrong is fine. I also want to see how much you want to say. Okay.
Okay, sir.
Okay. Anything further?
So can we comment on a similar construction on UN by SUN? Does it make sense at all?
Fine. Why not? Let's just check. First of all, UN is a set of all unitary n by n matrices, right? And first of all, you have to check whether SUN is at all a normal subgroup of UN. Step 1 then is to check that SUN is at all a subgroup of UN. SUN, of course, are those with determinant 1. And these are, of course, those with Chobe, U dagger, U equal to identity. Okay, fine. Now, what would you do next? You have to check whether it's a normal subgroup, right? Which means you have to show that if you give me any matrix, let's not call it U, let's call it something else, let's call it V. Give me a matrix V which belongs to UN, arbitrary matrix, You want to form V SUN. This, of course, is a whole subgroup, V inverse. And you want to check whether this is the same as SUN. Oops. The autocorrect feature. Is this clear to everybody? That's what you do every time. When you want to, that is for all V belonging to UN, V SUN, V inverse will have to be the same as SUN. That's what you want to show, right? However, you don't even have to show this much. All you have to show is V SUN, V inverse is contained in SUN. If that is what you can show, that is what you manage to show, then you are sure that SUN is a normal subgroup. Everybody is aware of this. I did discuss this in the lectures, and I hope everybody understands why this is correct. Although you really need to show this, showing this is sufficient. You don't have to go all the way as to show equality. Is that okay with everybody?
Just taking the determinant of 5.
No. First question is, determinant is relevant for this. I'm talking about a general thing. That the definition of a normal subgroup is for all G belonging to capital G, Gn G inverse is equal to N. That's the definition. But all you need to show really is for all G belonging to capital G, GL G inverse is a subset of N. That's all you really need to show. Remember, equal to means it works both ways. Gn G inverse is a subset of N and N is a subset of Gn G inverse. That's how you show two sets are equal. That's the easiest way of showing equality of sets, showing that both are A is contained in B and B is also contained in A. But for the definition of a normal subgroup, what you demand is for all G belonging to capital G, small g, N, G inverse is equal to N. That's what you need. But what you need to show is a weaker thing. You don't need to show the entire thing that is equal. You just need to show Gn G inverse is a subset of N. That's enough. Can anybody see why? Is everybody clear about why that is true?
We can just multiply by like G inverse on the left and G on the right.
Yeah,
So
actually it's a bit okay. What you really should start with is something like saying because this works for all G, it also works for G inverse, so it's also true. If this is true, then G inverse in G, which is what you get when you replace G by G inverse here, should also be contained in N, because this works for all G. It also works for G inverse. And then you left multiply by G, right multiply by G inverse, and show that this works. This, of course, actually presupposes something. It presupposes that you know this result. If A is a subset of B, then GA is a subset of GB, or AG is a subset of BG. These are trivial results, and hence also if A is a subset of B, then all these follows. Also GA G inverse is subset of GB G inverse also follows. These are trivial things, but you should check whether you understand them thoroughly first. Then the trivial results if you understand what you are really doing there. Okay, having said that, showing that this is a normal subgroup is trivial because any matrix which belongs to the left-hand side here, any matrix has to be of the form VS V inverse, anything which belongs here, where S belongs to SUN. And if you take the determinant of this, it's trivial to show that the determinant of this is determinant of V times determinant of S times determinant of V inverse. And determinant of S being 1, you simply get 1. Right? Okay. So that of VS V inverse is 1. And then I'm still here, right? Okay. And that means VS V inverse, every element of this is an SUN matrix. So V SUN V inverse is contained in SUN. That's what you have really proven, right? That every element of the set on the left belongs to the set on the right. So one is contained in the other. Done. And that's all you need to show is a normal subgroup. Fine. So UN, oops, by SUN, okay, this makes sense. Remember, the quotienting operation does not make sense. That is, does not give rise to a group. You can always say, okay, I just take all the courses together and form a set out of them. But that will not give a group in general. It will give you a group only if what you're quotienting by is a normal subgroup. In this case, this makes sense. But can anybody tell me what group will this be isomorphic to?
Sir, Z2 mod 2 mod 2.
You say Z2.
Z2 modulus 2.
When you say the group Z2, you automatically imply modulus 2.
Oh, right. I guess.
Okay,
Yes.
is that correct?
But sir, I mean, for this UN, we need a determinant of mod square is 1, right? So, I mean, there are like I mean, what I mean to say is, determinant 1 is
Okay,
one of
first
the
of all, before you go any further, this is wrong. Okay, so you started your but, that's fine. ON by SON is Z2. When I say group Z2, I mean the set Z2 with the modulus 2 or addition being the operation. Okay, that's always the conventional statement to make. So you don't need to say Z2 mod 2. This is correct. UN by SUN is not Z2.
R plus.
What is it? So what is being said is UN by ZUN is R plus. Why?
Sir, in some sense, I mean, what I feel is this consists of cosets which have this determinant e to the power I delta. So,
okay.
I mean that is the way I can envision them. I mean, like for the SON thing, we had 1 and -1, but this has like this continuous thing. I mean, e to the power I delta, where delta is continuous. So all of them are elements of this UN. Sorry, UN.
Yeah.
So in that sense, I mean, I feel it should be R, but I don't know about plus. I mean,
no, if it's R and you want the group out of it, it better be plus, because that's what makes R into a group, right? But okay, let's be a bit more concrete. Zero shouldn't be there. Well, if 0 is not there in R plus, then it's not even a group. Okay. After all, 0 is the identity element in R plus. But you may of course say it's not R plus. It's not R at it's not plus, it's not R at all. But if you're saying it's plus, 0 had better be there. Okay. Okay, let me just see this in a bit more detail. First of all, the important thing is what are the elements of UN? So elements of UN by SUN. These are the cosets, right? So coset of any particular, say, so a typical element will be V SUN. What is this? The set of all elements of the form VS where S belongs to SUN. Right? So what? So of course, remember, being in the same coset is an equivalence relation, as we have explained several times. An equivalence relation usually means some kind of equality. There has to be some property every element shares. Okay. Yeah. So that's some property. You might even say some property is as trivial as they belong to this particular coset. That's the property. Done. However, in this case, there's a simpler property that you can all talk about. Any element, any matrix VS, as was just commented right now, has one property in common, which is a determinant. Right? Because S belonging to SUN means determinant of S is 1. So every coset, every element of this coset has the same determinant as V. In fact, the converse is also true. If a matrix has the same determinant as V, it has to be in this coset. Is that clear to everybody? If a matrix is in the coset of capital V, it has to have the same determinant of V. That's easy to prove. Slightly less trivial, but quite easy, is the statement that if a matrix has the same determinant as V, it is in this coset. So basically, a given coset is essentially identified by the determinant of any one of its elements. Which one? Doesn't matter. Any one will do. Okay? Clear? So are there any questions about this statement? Let's take it in steps. Everybody clear about this? Yes? No? Maybe? I need a response. Okay, if nobody says no, then I'm assuming everybody has understood what I've said right now. So that essentially means that there is obviously a one-to-one correspondence, and is at a set theory level, not necessarily at a group level as of now. I'm not claiming it's an isomorphism, but definitely there's a one-to-one correspondence between a coset VSUN and determinant of V, right? But what values can the determinant of V take? That's important. Since V dagger V is identity.
Non-zero real number.
Yeah? Yes, yes.
Non-zero real numbers?
No, in fact, not at all.
Complex numbers with magnitude 1.
Yes, sir.
Exactly. I think when you said non-zero real numbers, you're confusing with GL and R, which is any invertible n by n R matrix. And this is, of course, a very special case. All the V's here belong to UN, remember? These are usually matrices.
Yes, sir.
So Z V mod square has to be 1, which means Z V will be of the form into the I alpha, where alpha is a real number. Okay? Right? Is it okay? Now comes the question: so e to the I alpha, this set, e to the I alpha, alpha goes to real numbers. This is a set, of course. What operation do we supply? So when you take two elements V1, V2, and V1, V2, of course, are matrices, but V1 will give rise to a coset V1 SUN, V2 will give rise to another coset V2 SUN. Okay? So this will give you the I alpha 1 as a corresponding number, some complex number with modulus 1. This will give you the I alpha 2 with some complex number.
Sir,
Yeah.
sir, this has in some sense a periodicity, so it cannot be R plus. I mean,
Okay. Good.
so I mean, so alpha, I mean, as it goes, I mean, we'll come back to again.
So
I mean,
first of all, alpha, if you say alpha goes over R, that's fine, but that will not be then this will not be a one-to-one correspondence.
Yes, sir.
So
The correspondence between okay, by the way, correspondence between this and dead V is 1-to-1. No problem there. But correspondence between dead V and alpha, between dead V and just the number alpha, okay, which belongs to a real number, that is not 1-to-1. That's one too many. Many different alphas will give rise to the same dead V, right? Is that okay? Is that okay? Yes or no?
yes, sir.
Yes.
Sir, so is
Actually-
it like 0 to 2 pi alpha belongs to 0 to 2 pi.
Or any interval, or better would be to say R, instead of taking R, you quotient out R by 2 pi. That is, real numbers which differ by 2 pi are all identified together. Okay? That's what this notation really means. And when you define addition, you define addition modulo 2 pi.
Sir, we can just define it from S1 only. Then it would
Yeah.
become 1.
This is actually S1. R quotiented by 2 pi is exactly what S1 is. S1 being the circle. So basically, unit, so instead of saying this, if you just said all Z belonging to C, where mod Z is 1, that's what you really meant, right? That's really the circle S1. But the operation on the circle is fine. This set under multiplication is closed. It forms a group under multiplication. Right? If you multiply two complex numbers whose magnitudes are 1, you end up with a complex number with magnitude 1. The multiplication, of course, is associative because multiplication of complex numbers anyway is associative. Then you have this identity, which is 1, which is, of course, in the set. And the inverse of Z also has modulus 1, so it's somewhere on the circle. So basically, what the correct answer, precise answer to this would be UN by SUN is S1. The group S1, which is basically the set S1. Remember, we often deliberately confuse between the name of the group and the name of the set underlying it. S1 is a circle, which is the set of all complex numbers with modulus 1. But if you supplement the S1 with complex number multiplication, then you get a group. And that group is also called S1. So strictly speaking, the correct answer to this would be UN by SUN is isomorphic to S1, the circle. Well, R plus actually is homomorphic to UN by SUN. Right? Because can easily show that the map that we were talking about, give me any real number alpha here, I get an e to the I alpha, right? From here. Alpha maps into e to the I alpha, no problem. That's a complex number of magnitude 1. And this will immediately map onto a particular coset VSUN, where V is any matrix with determinant e to the I alpha. So you can, of course, find a map from alpha to this, and you can easily show that that map is a homomorphism. It's a trivial thing to do. But it's also true, as you just now pointed out, that this map is many to 1. By the way, can anybody tell me what is the kernel of this map? You know what a kernel of a map is? Yeah. Any questions about that?
Sir, I had a question, which is this S1 that we're talking about, shouldn't it also be isomorphic to just rotations in 2 dimensions? So that will be SO2, right? Isn't it more convenient to speak of it in those terms?
Depends on what you want to really do. Not always, right? Depends on which aspect you really want to look at. Complex numbers are easy. Look, complex numbers with magnitude 1 are much easier to deal with algebraically. Okay. Rotations into dimensions are easy to visualize geometrically. Whichever way you want to put it, it's a circle anyway. So whether you want to interpret that as an angle theta, which is a real number which goes from 0 to 2 pi, or which can take arbitrary real values, but then you have to quotient out 2 pi. By the way, this homomorphism that we are talking about, the homomorphism which goes from R plus and maps it into UN by SUN. Or forget about this, because in between there's this R plus maps to S1, S1 maps to this. This part is actually an isomorphism. So strictly speaking, what is UN by SUN is the same as a circle with the group structure imposed on it. But this one is many to 1. which is why this map is also many to one, and hence it's not an isomorphism, it's just an homomorphism. But can anybody tell me what is the kernel of this homomorphism? Well, I'm not sure whether I've not defined kernel yet in a lecture that I have uploaded. The kernel is going to come in the next lecture. But the kernel of a homomorphism simply means all elements of the domain which map onto the identity of the range. That is, in this case, or S1, which remember are set of all complex numbers with modulus 1, S1 is simply the number 1. The identity in S1 is just the number 1. And it's the identity of multiplication.
0,
Yeah?
2 pi, 4 pi, dot, dot, dot.
So the kernel of this homomorphism is actually 2 pi times is 2 pi z or 2 pi z, which
Yes.
simply means to take the set of integers, multiply them by 2 pi. Okay?
Yes.
And the precise statement that we should make, in fact, this is something which we are going to talk about in the next lecture, so not relevant for today's class test. But in the next lecture, lecture 7, we will talk about isomorphism theorems, which tell you how to change homomorphisms into isomorphisms.
Sir,
And there you will learn that this is, okay, there you will not learn, but there you will learn the basic which tells you why this is true, but you all know what this is, right? This really means you take a real line and you take points 2 pi apart and map them all together. So it's like rolling up the real line where points which are 2 pi apart all fall on top of each other. And that of course gives you a circle.
sir,
So whether you, yeah, go ahead.
I mean, sir, I'm getting this feeling that, I mean, in an isomorphism, only the identity can go to identity and no other element can go to the identity, in the sense that the kernel should only include the identity. So,
Of course.
so when you,
By the way,
when,
let's understand why that is true. That is true basically because isomorphisms are one-to-one, right?
yes, sir, yes, sir.
And one important property of homomorphisms, something which we
Is
have
that
already explored is the identity has to map to the identity. So because isomorphisms are one-to-one, the only thing which maps onto the identity has to be the identity.
Yes,
Yeah.
sir. So, sir, when you're using this equivalent relation, what you are actually doing is you are identifying points on the interval of 2 pi. So you are effectively reducing the, I mean, I don't know, I mean, in some sense you are reducing all of this kernel to a single point.
Exactly.
So,
By the way, that's
understand
actually
the-
perfect. That's exactly the intuition which you should have. Homomorphisms basically have this situation. In fact, thank you for pointing that out, because then I will also, okay, I will not include that in the next lecture because that's sort of trivial now if I explain it. But the basic idea is a homomorphism is many to one, typically. Could be many to one, could of course be one to one as well. Then it would be an isomorphism. But in a homomorphism, what happens? Typically, multiple elements can map onto the identity. But if you somehow actually take all of those points together, identify them as a single element, you essentially ensure and do it consistently with the group multiplication law. What you do is you ensure that only one element. So basically, in a way, what you're saying is, okay, this point was mapping to e to the I alpha. This was also mapping to e to the I alpha. This was also mapping to e to the I alpha. Say all of them were mapping to same. They were different alphas, but alpha plus 2 pi, alpha plus 4 pi, all of these were mapping to the same complex number. So this prevented the mapping from being one-to-one. Then what do you say? You say, okay, why don't you just identify all these elements and call them the same element? That's exactly what quotienting is. You essentially identify a bunch of elements together and say, okay, they look like different elements in R, but now I'm going to put all of them together in one bunch and call them one element of my new group. And that essentially is exactly how you end up with the homomorphism, which originally was a homomorphism, become an isomorphism. There's some more mathematics to be gone through before that, but basically what you have told me right now is a basic idea behind what is called the second isomorphism theorem, topic of the next lecture. It simply says that if F from G1 to G2 is a homomorphism, then G1 quotiented by kernel of F is actually isomorphic to G2. By the way, you've already seen this happen without using the words, because you have already seen what this is, right? What is this? GLNR by SLNR? This was? Right? But there's a very simple homomorphism between GLNR and this. This is what we described, right? What is the most obvious homomorphism you can have here?
The determinant.
The determinant map. You take any two matrices and take the determinant. Det M1 M2 is det M1 times det M2. So completely obeys the group multiplication structure. Of course, when you do det M1 M2, the M1 M2 is matrix multiplication, and then you are doing the determinant. On the other hand, you are doing det M1, getting a number, det M2, getting another number, ordinary number, and multiplying them together. That's a multiplication of ordinary numbers. But det respects that, right? You can do the det first and then multiply, or do the det after multiplying. Fine. So this, but det of course is a homomorphism, because evidently many different matrices will have the same determinant. But if you remember, exactly what are we doing here? GLNR by SLNR. When we are taking the cosets are essentially collections of matrices, each of which have the same determinant. All of them are clubbed together. And all you are saying here is this. Find many elements we are mapping into the same element here. So that's why this could not be an isomorphism. So how do you prevent that from being many to one? You just say, okay, take all those many which we are mapping onto something, onto the same element, club them all together, call them the same element. That's it. But what is important, what is really very important here is this. If you just manage to club all the elements which we are mapping to the identity together into one, that is sufficient to essentially ensure that this will work for every element. That is the non-trivial part. But notice that the kernel of det, what is that? Now that you know the definition of kernel, tell me what the kernel of det is.
SLNR.
Is everybody clear about this? So this is, of course, the kernel of the det map is simply all the elements of GLNR which map onto the identity of R set minus 0, commas, times. And that identity, of course, is 1, the number 1. So kernel of the det map is simply those matrices which map to 1 under the determinant map, or which in simpler language simply has determinant of 1. Which of course is exactly what SLNR is. Right?
Sir, I think in order to tell this, shouldn't we show that the kernel of a map is a normal subgroup of the...
Of course. It should.
Yeah, okay.
It's a trivial thing to show, but it should be shown.
Oh, okay, cool. Huh.
And that is exactly what the next lecture is all about. So I don't really want to give you the next lecture now. I've gone through some trouble of recording it, right? So the only reason why I did not upload it is that you have an exam today, so get some time off before that. And because I did not want to confuse you with whether that is also in the exam or not. Yeah, you have to. That's perfectly right. You cannot just say GLNR by, cannot say G1 by CUDF without showing that CUDF is actually a normal subgroup of G1. So to start by showing that the kernel is actually a subgroup, then showing that it's not only a subgroup, it's a normal subgroup, then proving two theorems, stating and proving two theorems. The Isomorphism Theorem One, which is the statement that if, by the way, what was said a while ago is that if F is an isomorphism, the kernel has to have only the identity, nothing else. Right? Is that okay?
Yes, sir.
Yes, sir.
But the converse is, okay, that is trivial, but that and its converse, that is an if and only if statement, is actually Isomorphism Theorem One. Okay.
As in, if the kernel has only the identity, it implies that.
Then it implies that it's an isomorphism. Okay. So notice one thing, saying that this is this is actually where the group structure, the group theoretical properties come in very handy. If you had any arbitrary map which just said, okay, say some arbitrary map which maps the identity E1 into E2 and it only maps E1 to E2, that by no means tells you it's 1-to-1, right? Is that okay? You do understand this, right? Because suppose I had three elements here, E1, say E1, and this is E2, and maybe this is A, B, and here you have, say, C, D. I know E1 is the only element which maps to E1 on an arbitrary map. Does it tell me that this is impossible? A and B both mapping to D. Will that prevent? Will E1 going to E2 and E1 only going? E1 of course can go only to one element, but
if
only
the map
E1
is
going
a
to E2.
homomorphism, then it will prevent it.
Yeah, the important part is the homomorphism and this together tell you that it's 1-to-1. The homomorphism property is important. But arbitrary map, of course, you can definitely have this. You can have a picture. This is a perfectly legitimate map, right? Only one E1 going to E1, but all other elements going to the same result. That's always possible. But that will not be possible in a homomorphism. So because we are dealing with homomorphisms, then the kernel being only the identity actually proves that it's an isomorphism. That's theorem 1. And theorem 2 simply tells you that if kernel is not an isomorphism, even then you can make an isomorphism out of the homomorphism simply by managing to identify all the different elements which map onto the identity, just bunch them together. And that's it. So the feeling that was talked about a while ago is perfectly right, except that you have to go ahead and prove this. But this is a very important it's important to have that feeling. That actually gives you an intuitive understanding of what is going on. Okay, but unfortunately, we are spending way too much time in what is going to come in the next lecture, rather than on any questions you people may have about things which we have already discussed and which will be asked in the exam a while later. So if I'm going to assume that whatever we have studied so far is perfectly okay, everybody has understood everything, I am happy with that. But
so can you give some questions right now? I mean, to solve. I mean, similar to
sorry,
those
I
that
couldn't. Sorry, I couldn't hear you. Could you just go slowly?
Yes, I told, can you give some, I mean, problems to solve right now? I mean, similar to
no,
those
I can't. I won't, because unfortunately I have a finite number of questions and I don't want to give them away. Come on. The questions will be easy. Okay, today the questions will be laughably easy. Okay. And if a question seems difficult, there can be only two explanations. One is I have mistyped the question, in which case you say write whatever you want. And the other one is you're simply misreading the question. You're reading too much into the question. I've already given you some problems, right? Let me just tell you that the questions today will be even easier than that. They will be ridiculously easy. This is the first class test, so I'm making this ridiculously easy. Okay, if anybody from my quantum mechanics course is listening in, you shouldn't be. You should be preparing for your exam today. Your exam will not be that ridiculously easy, because that will be essentially based on preliminary topics which has already been studied in the previous 2 semesters. That's the difference between that exam and this one. Okay, I hope nobody is listening in which case this is a wasted statement, but still.
Sir,
Yeah.
so there was a question in problem set 4 that the order of G divided by the order of H is equals to 2. If that happens, then all the right cosets of H must be same as the corresponding left coset. So how do we prove that? I couldn't make it out actually.
Okay, that's a good question. Although that's a very, if you think about it, it's
Like
really rather easy.
I made it with the example, the previous one with
Yeah,
that square
the
set.
example was of course there, right? For the
Yeah, but
S3.
trivially, how to prove that?
Yeah. Okay, so it's really rather trivial, but the trivial thing is this. One coset, of course, is H itself, right? Sorry, not the mod, just H. What are the cosets here? I'm saying order of G divides order of H, and of course that's always true. That's Lagrange's theorem, but the ratio is 2, right? So what happens? H has elements H1, H2, and say Hn. One of these have to be the identity, of course, right? So the coset with H1, what will that be? And
H1 itself, the capital H,
yeah,
because it's an equivalence class.
and if you take any one of the H's, H1, H2, Hn, you are going to get capital H itself, right? Okay, so the left cosets will all be capital H. What about the right cosets?
They'll also be H itself.
So in this case, the left coset and right coset will be equal, but that's trivial, right? That happens for every group. If you take elements from capital H itself, then whether you put that on the left of capital H or to the right of capital H, you will end up with capital H itself. But now pick an element H prime. I'm calling it H prime deliberately. Okay, maybe I should call it something else. Anyway, I'm calling it H prime to show that H prime is not one of H1, H2, Hn. Okay. Right? So this is a coset. You agree? So H prime times capital H prime is not in H. So H prime times capital H has to be a coset, of course. That's the definition of what a coset is. But can H prime capital H contain capital H prime? Is it in or out?
It is in, because H has the
Has
identity.
identity. Yes.
Yeah, since H has the identity, H prime capital H has to have H prime, right? That means H prime H intersection with capital H. Okay, not intersection. H prime capital H, first of all, which means H prime H is not H, right? Is that clear?
Yes.
Two sets can be equal only if they have exactly the same elements. H prime H has H prime, capital H doesn't. So what does it tell you about this intersection?
So that will be a null set, no? Like if H prime H doesn't contain any of the H elements,
Yeah.
so that will
Well,
become a null set.
yeah, it is a null set. Good. So there is H prime H does not have any overlap with H. But how many elements does H prime H have?
The same number of elements as H.
So what can they be?
It should be another, the other cos set that has been divided from the line.
Look, G has 2n elements, H has n elements, G has 2n elements. The n elements which are in capital H cannot be in H prime capital H.
So these are the elements that are in G which are not in H.
Exactly. So H
G
prime
minus.
H has to be those elements of G which are not in H, G set minus H in this case. Has to be exactly the same, right? In general, for an arbitrary group, you would have said H prime H, if this condition had not been true. What would you have said? You would have said H prime capital H has to be a subset of G set minus H. Because elements here have to be in G and definitely cannot be in H, because if two cosets are not identical, they have to be disjoint.
Sir,
right? Yeah.
just one. I mean, there are two distinct left cosets here, right? I mean, when we say two left cosets, I mean, are we erring somewhere? I mean,
so here you have H and G by H. These are the two distinct left cosets. Yeah. But that was not the question. The question is, if you take any element from capital H, the left coset HH will be H, right? And if you take any element from outside capital H, then this has to be the complement. So far, so good, right? When you say it's a normal subgroup, you mean the left cosets and right cosets are identical. That is, this has to be correct. That's trivial. That is always correct for every subgroup. But it also has to be correct for this. Same argument. Is that clear? I don't care whether H is normal or not. Yeah? Yes?
So what we are trying to say is that if we take an element outside H and give a left coset like H prime H, then it will be the coset of G which is not contained in H.
Well, it will be a set of elements in G which is not contained in H.
Right? Yeah.
It has to be because you need n elements and there are only two n elements in G. None of these n elements can be in H. So it has to, in general, for the statement would be this. Right? If H prime does not belong to capital H, then H prime H has to belong to G but cannot belong to H, so has to be somewhere in G set minus H. In general. And that's also true for H prime. H prime has to belong to H G set minus H. This is true for all groups, right? But because in our case, mod G by mod H is exactly 2, that means G set minus H has exactly as many elements as H prime H has. So it has to be the same set. So that's why H prime H has to be G by H, H prime also has to be G by H. There are only two choices. You can, if you think about it, if you look at the example, here you had EDF as your 3-element subgroup in the 6-element EABCDF S3, right? What were the cosets? Left cosets were EDF and ABC. So if you took E with this, you got this. You took A with, instead of that, if you took A with this, you end up with ABC. But whether you take A or B or C doesn't matter, you get ABC. But that's for the left coset. For the right coset also, you have no choices. The left coset would also, right coset would also have to be EDF if you take it with E, or D or F. And when you take it with A on the right, you have to get ABC. In this case, it's really trivial. You don't have any other elements to play with. That's all there is to it. Okay. So left cosets have to be the same as right cosets simply because you have no other choice. Yeah.
But this means it is
because
normal.
they have same number of elements.
Look, all cosets have to have exactly the same number of elements as the subgroup whose coset they are, right?
No,
So
I meant to say that as H has n number of elements and we have that condition G by H is 2, So that means they are divided in
So,
n and n only.
so G,
So that's
right.
the point.
There are only two parties. Both partitions have all partitions by courses have to have exactly n elements, and here you have only two choices. The important thing to note is right courses have to be disjoint. So the point is h times a times h cannot be h times a also cannot be h, right? In this particular example, because a does not belong to h. And then there's only one choice. AH has to be the other elements. HA also has to be the other elements. So AH and HA have to be equal. Of course, if you have more than, say EA, if you had, say, mod G by mod H equals 3, which also, of course, is a possibility for that particular example that we talked about, for S3, right? This is a subgroup, right? Now, of course, its cosets with A and E are both EA. But cosets with B, for example, must have one more rotation. I'm not forgotten whether it's B or D. But either way, it could be one. But now there are four possible elements it could be from, and there are only two which you have taken. So now there's no guarantee that the left and right cosets have to be the same. By the way, I'm not saying by any means that mod G by mod H has to be 2 for left and right cosets to coincide, right? Because for all normal subgroups, left and right cosets coincide. All we are saying is, in a finite group of even order, if you have a subgroup of order this by 2, which you always have, by the way, that subgroup has to be normal. Anybody who has studied abstract group theory would know that Silov's theorems actually sort of go much deeper into these things. But this is a very trivial result. You don't need any advanced mathematics for that. All you need is there is no choice.
Oh, sir, I have a question.
Yeah.
About inner and outer automorphisms.
Mm-hmm.
So you defined it that it arises from conjugacy classes, right?
Well, I defined them. I didn't decide anything.
I mean, I said defined.
Okay, sorry. I thought
Yeah.
I said decided.
So I mean, how does it? Conjugacy classes are equivalence relations at the end of the day, and how does that partition the entire set of automorphisms? Does it partition as inner and outer only, or how does it happen?
No, I don't really see whether what you're saying is right. Conjugacy is an operation, right?
Yes,
From
sir.
that you get conjugacy classes. That's one thing. And conjugacy acts on the group itself and produces an automorphism on the group.
Okay.
You use conjugacy in both cases, but they are two different things, really.
Oh, okay.
Okay, but in a sense, you are right in the sense that you can use the conjugacy inner automorphisms to just find out what the conjugacy classes are. If you apply, say, IG on the entire set capital G, that will actually give you the conjugacy class of G, right?
Yes, sir.
However, IG is a map which acts on individual elements. If you apply it on the entire set, you end up with all those elements which are conjugate to G. So that way you get the conjugacy class.
Okay.
But the inner automorphism, of course, is a map which maps G, elements of G to other elements of G. They're related, of course, but I'm not really sure how you will connect the two together that way.
Oh no, I was just talking about the conjugacy classes and how they're related to.
Yeah, but this is the relationship. You take IG, apply it, take the inner automorphism corresponding to the element small g, apply it to all elements of capital G. So that's exactly what we did when we talked about conjugacy classes, by the way. When we had this table, when I found out the conjugacy class of S3 in a lecture before we introduced the inner automorphisms, I even had this table with the heading IA, with columns, rows headed IA, IB, IC, and so on. I did mention there that those are inner automorphisms, but we will talk about them later. But IA is simply a map which maps G into AGA inverse. IB is something which maps G into BG, B inverse, and so on. And if you apply IA on the entire set, what you're going to get is the conjugate. The resulting elements will be the conjugacy class.
Okay, sir.
But that's sort of trivial from the definition of conjugacy class, right? All elements which are conjugate to this. Okay. Anything further? If not, we will see you at 2:30. Oh, I will not going to see you at 2:30. You're just going to log in into Wheeler, work your answers, submit in time, hopefully. And by the way, submission, even partial submission can give you marks. So if you don't complete, and don't try submitting at 240 or 250 or 260, because the system may simply not allow you to do that. Okay, any further questions or comments or statements before we can just log out? If not,